So we are going to be talking about resistor combination techniques for today. This should largely be a review. We are going to explain why resistors combine the way they do using Kirchhoff's current law and Kirchhoff's voltage law, work a couple of examples, and then move along to a lab assignment. So let's first consider what happens when we have resistors in series. So let's say that I have some DC voltage source Vs, and it is connected to a network that contains multiple resistors connected in series. Let's call this guy R1, this guy R2, all the way out to some nth resistor that is also connected in series. Like so. This is an example of a single loop circuit like we dealt with in class on Wednesday. So we can say pretty easily that there is a common current that's flowing around this single loop. And I'm just going to call that I. And I'm going to make an assumption here that isn't really an assumption. I'm assuming that I is going to be flowing counterclockwise around this loop. And the reason why I'm making that particular assumption is because Vs is the only source in my circuit, so I assume it's the thing that's supplying all the power. Okay? This common current I will cause a voltage drop over each one of these resistors. So we can call this voltage drop VR1, this voltage drop VR2, all the way out to this voltage drop VRN, where I've chosen those particular polarities for those voltage drops across my resistors, such that the current is flowing into the positive polarity terminal, and therefore I get to use the simple V is equal to I times R representation of Ohm's law. Effectively, I chose this polarity to make sure I don't have a bunch of random negative signs all over this. So if I write a Kirchhoff's voltage law equation around this loop, what I will find is that negative Vs plus VR1 plus VR2 all the way out to VRN is equal to 0. And then I'm simply going to move that Vs term to the other side of the equal sign. So this would look like Vs is equal to VR1 plus VR2 all the way out to VR sub n, like so. Are we all okay with the minimal amount of algebra I've done to this point? So now what we're going to do is exactly what we did on Wednesday. We are going to express all of those resistor voltage drops in terms of that single unknown current that flows through this entire loop. So using Ohm's law, we could say that VR1 is simply I times R1, VR2 is I times R2, and so forth until we get out to I times R sub n. And we can now observe that we have a common factor of I flowing through all of these elements. And so if we take that out, or factor that out, we have I times R1 plus R2 all the way out to R sub n. Now, yesterday, when we learned about Ohm's law, we used our experiment that we did at the end of Monday's class to figure out what that relationship is. So we have something similar here, okay? we have a voltage, Vs, and we have a current, I. And so the ratio of Vs to I is the resistance that is seen by that voltage source, okay? Effectively, it is the equivalent resistance that we would see between this terminal here and this terminal here, where we are considering that series chain of resistors to be our material under test, like we were dealing with at the beginning of Wednesday's lecture. So we can define our equivalent resistance, Req, in this case, to simply be the ratio of Vs over I from Ohm's law, which is thus just R1 plus R2 all the way out to R sub n, or in a slightly fancier mathematical notation, the summation from I is equal to 1 to n of R sub I. So effectively, if we have resistors in series, we can combine them into an equivalent resistance simply by adding the resistor values together. Nothing different than you learned in your earlier classes, but we have a more formal approach of why we can do that now. Any questions on how we combine resistors in series? Hopefully pretty straightforward. All right, let's move along now to resistors in parallel. So now let's consider a single node pair system where we have some current IS connected to multiple resistors connected in parallel. So here's our resistor R1. Here's our resistor R2. And let's consider the case that we have N resistors in parallel. So here's R sub N. Because all of these elements are connected in parallel, they will all share a common voltage, which I will simply call V. And we are going to assign currents to each of our resistors. So I'm going to call this IR1. I'm going to call this IR2. I'm going to call this current IRN, where the direction of the current that I have chosen is that the current is flowing into the positive polarity terminal of our voltage V, so that, again, we don't have any pesky negative signs or anything like that to worry about. If we apply Kirchhoff's current law to this system, and let's use the formulation current flowing into the top node is equal to current flowing out of the top node, this will give us IS is equal to IR1 plus IR2 all the way out to IRN. Using Ohm's law, we can express all of those resistor currents in terms of that common voltage V, exactly like we did on Wednesday. And so this becomes V over R1 plus V over R2 plus V over Rn. I'm now going to factor out that V. And so we'll have V multiplied by 1 over R1 plus 1 over R2 all the way out to 1 over Rn. Now I can figure out what the equivalent resistance is that is connected to my current source. Again, using the exact same thing we did just a moment ago, okay? So the equivalent resistance in this case is going to be V divided by IS, which is going to look like 1 over R1 plus 1 over R2 plus 1 over R sub n, and then we take the reciprocal of that sum. So I'm raising it to the -1 power, or, sorry, scrolled slightly too far. In slightly fancier mathematical notation, our equivalent resistance is 1 over the sum from I is equal to 1 to n of 1 over R sub I. So to combine resistors in parallel, we take the sum of the reciprocals, and then we take the reciprocal of that result. All right, so this is how we handle an infinitely large number of resistors. This works for 2 all the way out to infinity. Now let's talk about a very special case when there are exactly 2 resistors in parallel, okay? I'm going to show you guys a shorthand for calculating resistance, equivalent resistance here that you may or may not be familiar with, but I am going to use it extensively, and so I want you to know where this is coming from. So let's say that I have a simple network containing exactly 2 resistors in parallel. Call this one R1 and this one R2. And I'm trying to find the equivalent resistance as I look in through this set of open circuited terminals. Using the expression that we just derived, the equivalent resistance that we would see should be 1 over R1 plus 1 over R2, which is absolutely correct. That's annoying to do. So what I'm going to do now is I'm going to multiply that first fraction by R2 over R2. I'm going to multiply this second fraction by R1 over R1. So I'm just using a fancy formulation of the number 1 in each case. And what's going to happen is now I will have 1 over R2 divided by R1 times R2 plus R1 divided by R1 times R2. And since both of my fractions in the denominator have a common denominator, I can add them together. So this will look like 1 over R1 plus R2 divided by R1 multiplied by R2. And finally, since we are dividing by a fraction, that is the same as multiplying by the reciprocal of a fraction. So we are just going to get R1 multiplied by R2 over R1 plus R2. This works for 2 resistors in parallel only. What I mean by that is that we cannot extend how this works to more than 2 resistors, okay? So if we had 3 resistors in parallel, it would not be R1 times R2 times R3 over R1 plus R2 plus R3. It actually can't be, the units don't work out, okay? If you ever have more than 2 resistors in parallel and you want to use this method, combine 2 of the resistors using this method and then keep doing that over and over again until you finally just have 2 resistances at the end to combine together, okay? Or, in my opinion, the much easier route here would be just to use the reciprocal equation and get it all done in one go. All right, how do we feel about the rules for combining resistors? Again, should be pretty much review. Maybe didn't know the math behind it, but arguably you do now. Let's put some things into practice, work a couple of problems, and then I will be done talking for the day. Okay. So let's start with this network. Okay. Bless you. All right. So this is our resistor network that we are going to try to simplify. This particular network contains multiple different resistors, some of which are connected in parallel, some of which actually I don't think any of them look like they're in series right now. And many of which do not fall into either of the 2 simple boxes. So what we're going to try to do is reduce this network down into a single equivalent resistance by performing combinations of combining resistors, okay? So let's start by finding the resistance seen between terminals A and C. So I'm going to call this RAC, okay? Now, what I like to do, you don't have to do it, but I encourage you to follow something like this, is label all my nodes like we've done in the past. So this red thing here, oops, I did not mean to erase that, is going to be node A. This pink thing here is all node B. This green thing here is node D. And this blue thing over to the right is node C. So if I'm trying to find the resistance RAC, what I like to do is put my A terminal on the left-hand side of my page and my C terminal on the right-hand side of my page, and then effectively play connect the dots with resistors, okay? So what I'm looking for is the different possible ways I can go from A to C. Okay? So for me to go from A to C, I have to go through the 100 ohm resistor, or excuse me, the 100 ohm resistor to node B. There is no other possible path that I could take, right? So I'm going to put node B, or excuse me, yeah, node B right here. And here's my 100 ohm resistor. And I'm going to put a check mark here to let me know that I've taken care of this path. Now, that's the only path from node A, so I'm effectively done with that step. To go from B to C, I'm obviously going to have to go through node D. So I'm going to place node D over here. But there are multiple different ways that I can go from B to D. I can go from B to D through the 50 ohm resistor. I can go from B to D through the 25 ohm resistor. I can go from B to D through the 75 ohm resistor. Daniel. You're exactly correct. When there are multiple paths to go from one node to the next, all of those paths are in parallel. You're absolutely correct. So I'm going to put between B and D 3 resistors in parallel. I have my 50 ohm resistor, my 25 ohm resistor, and my 75 ohm resistor. And I'm going to go check, check, and check. And lastly, I can go from D to C through my 200 ohm resistor, like so, and put a check mark here. Now, Aaron, what's your question? Fantastic question. I have left out the 125 ohm resistor. Why have I left it out, you may ask? The 125 ohm resistor is connected between node B and node B, which means it is in parallel with a short circuit or a wire. So what is the equivalent resistance of any resistor in parallel with a wire? It's 0, right? And we can mathematically prove it. Just as a very quick aside here, if we have a parallel combination of resistors, and one of them has a value of R, and the other one has a value of 0, then we're going to have 0 times R over 0 plus R looks like 0 ohms. Anytime we have a resistor connected on both sides to the same node, that resistor is shorted out and it does not contribute to our equivalent resistance. Okay. So from here, going back down to our problem, it should be fairly straightforward to see what we would do. The 50 ohm resistor is in parallel with the 25 ohm resistor, is in parallel with the 75 ohm resistor, so we can simply combine those 3 resistors in parallel. So let's take our calculator and do that. 1 over 25 plus 1 over 75 plus 1 over 50. I don't know why I decided to say them in that order, but I did. Looks to me like 150 over 11 ohms. So because those 3 resistors in parallel are between nodes B and D, we're going to erase all of them and replace them with an equivalent resistance connected between nodes B and D. So we take everything from B and D out, disconnect it from the circuit, figure out what the equivalent is, put that equivalent back in between B and D, and call it a day. So I'm going to erase all of these. Replace it with the equivalent 150 over 11 ohms. Now we can see that we have three resistances in series. 100, 200, and 150 over 11. So from that, RAC is 3,450 over 11 ohms. Sorry, the ohms should be out here, or 313.636. All right. This one was fairly straightforward. This is a resistor combination problem that I literally put on a previous exam. Okay. Now let's up the difficulty slightly and look at something from one of your homeworks. It's not as bad as some of the problems, but yeah. Okay. All right. So this is homework 3, problem 2 with slightly changed numbers, which we all get randomly assigned numbers anyway, so it doesn't particularly matter there. Which pair of terminals do we want to find the resistance between? Do we want to find it between A and B, B and C, A and C, B and D? Somebody give me 2 letters. A and D. All right. So this will be rad, apparently. That is a terrible joke. All right. Let us color our nodes. Right. This red thing here in the top left-hand corner will be node A. This pink thing here in the top middle will be node B. This orange node here on the top right will be C. Down here in the bottom left, we'll have a node that we have not yet labeled, so we'll have to do that momentarily. This guy down here will be D. And we have another node in the bottom right that is not labeled. So just for the sake of argument, I'm going to call this green guy over here on the left node E, and this blue guy over here on the right node F. Since we're finding the resistance between A and D, I'm going to put A on the left-hand side of my paper, D on the right-hand side of my paper. And I'm going to give myself plenty of room. All right. So let's start with the obvious thing. There is a direct path between nodes A and D containing the 50 ohm resistor. Okay. So we're going to draw that one first. So I'm going to slap my 50 ohm resistor here in the middle of the paper and connect A to D. And some of you, hopefully only 1 or 2, think we're done. We are absolutely not. Okay? We have to take into account the contribution of all of those other resistors as well. So what other ways can we get from A to D? Oh, and let me put a little check mark by this guy to indicate that we've used it. So an obvious path to me is for us to go from A to E to D. Let's do that one next. E is in the middle. To go from A to E, we have to go through the 100 ohm resistor. And to go from E to D, we would go through the 25 ohm resistor. How else can we go from A to D? Go through B, okay? So let's put B here in the middle. We can go from A to B through the 200 ohm resistor. And then we have multiple different routes we can go from B to D through. So let's start with the obvious one, the direct path through the 75 ohm resistor. So we've taken care of this guy and this guy. Now we could go from B to C to D. Where going from B to C would be the 40 ohm resistor. And C to D directly would be through the 250 ohm resistor. And I'll put the check box for those, so 40 and 250. And we could go from C to D alternatively by going from C to F to D. So let's put F here. And C to F is the 150 ohm resistor. And then from F to D is the 60 ohm resistor. And from here, we would just work our way from bottom to top, step by step, making any combinations we could. So for example, the 150 ohm resistor is in series with the 60 ohm resistor, so we could combine them to be a 210 ohm resistor placed between nodes C and D. Then that would put the 250 in parallel with the 210 and so forth, and we just work our way towards. Okay. I understand that this is a tedious process, but it works every time if you are careful. I am a jackass with a PhD, and I still do it this way 20 years after I learned it. Anytime I have any inkling that I might make a mistake, if I can't obviously see what the answer is, this is what I do, still to this day. All right, yes.
R of A to D, right?
Mm-hmm.
Would that be the same as D to D or any other combination?
Nope. Every other pair of terminals is going to have a different roadmap to get that resistance. So it would be entirely different. There might be some parts of it that are the same, but RA to D is going to be different than RA to B, RA to C, RB to C, all of that stuff, all going to be different resistances. Yeah, and so to approach any of those, you would follow this exact same thing. put one, the first one, the first terminal you're trying to find to the second term on the left-hand side, second terminal on the right-hand side, and then just play connect the dots with the resistors. All right, was there another question? All right. Let's do one more example here, tying this into circuit analysis. Okay. So here we have an 80-volt source. $30 ohm resistor, a 180 ohm resistor, $45 ohm resistor, a 70 ohm resistor, bless you, 22 ohm resistor, a 12 ohm resistor, a 7 ohm resistor, and that's it. And we want to know how much power is supplied by the 80-volt source. So every other time we've done any type of power calculation or anything like that, or at least the ones that we did in class on Wednesday, we were using KCL, KVL, Ohm's law, and all that kind of good stuff. We're going to wind up using Ohm's law in this case at the end. How we are going to approach this problem, which looks pretty difficult, is by finding out the equivalent resistance that the 80-volt source sees and lumping it down into a single resistor. From there, we know that the power absorbed, or excuse me, the power supplied by the 80-volt source is simply going to be the power absorbed by the equivalent resistance, which is just going to be V squared over the REQ that we find. Okay, so let's map out our different nodes. Let's throw some labels on things. So I'm going to call this red node A, this blue node B, and then this is C and E. We are trying to find the equivalent resistance between nodes A and B. So I'd put A on the left-hand side and B on the right-hand side. So how can I go from A to B? The shortest path that I see is from A to E to B. Okay. So let's throw E right here in the middle. And to go from A to E, we go through the 12 ohm resistor. And to go from E to B, we go through the 7 ohm resistor. I'm going to move node E to the right here just a little bit because there's only that one path from E to B. And I want to make sure that I have enough room for everything else that I'm going to do. All right. So we've taken care of this guy and this guy. Another way that we could go would be to go from A to D to E to B. So let's put D here. We go from A to D through the 70 ohm resistor. And then we go from D to E through the 22 ohm resistor. I'll check these off. Another way that I could go would be to go from A to C to D. But there are two different ways that I can go from A to C. So let's put C here. I can go, oops, that's not what I meant to do. I can go from A to C through the 30 ohm resistor. I can go from A to C through the 180 ohm resistor. This guy and this guy. And then lastly, I can go from C to D through the 45 ohm resistor. And I believe that takes care of the only resistance that we had left to take into account. I've got a check mark by everything. Let's just double check here. 4, 5, 6, 7 resistors. 1, 2, 3, 4, 5, 6, 7 resistors in the way that I've drawn it out. And from here, we would simply go about our simple combinations, right? So what's 180 in parallel with 30? You guys have calculators? $25.714. All right, so I'm going to replace these two resistors with a single resistance between A and C. That is 25.714 ohms. Now I can see that I have two resistances in series, excuse me, 25.714 is in series with 45. So I can simply add 45 to that. And now I'm going to have a new resistor placed between nodes A and D. Which is going to look like 70.714 ohms. Now the 70 and the 70.714 appear as if they're in parallel. So that's going to look like 35.178. This 35.178 ohm resistor appears to be in series with the 22 ohm resistor. So I can place between nodes A and E a single resistance having a value of 57.178. Now I see that the 12 ohm resistor and the 57.178 ohm resistor are in parallel, so I can combine them. Which looks like 9.918 to me, if I've done the math correctly. And then lastly, I can say that RAB is just those two resistors in series. So I will add 7, giving me 16.918 ohms. From here, the voltage, or excuse me, the power absorbed by my resistor network, P REQ, is just my voltage squared divided by the resistance RAB, which is going to be 80 squared over 378.286 watts. And the power absorbed by my resistor network has to be the same as the power supplied by my voltage source because of Teligent's theorem, which we learned on the second day of class. And we're done. So this is how we incorporate resistor combination techniques into actual circuit analysis, okay? We simplify the circuit down to something that we know how to do, and then we fall back on our regular things like KCL, KVL, Ohm's law, and all that kind of good stuff. All right, unless anybody has any questions, which I would be more than happy to answer, I am done lecturing for the day. We have a mini lab up here. All it requires is multimeters, breadboard, and these 4 resistors, no power supplies or anything like that. You might need a couple of wires. Mason, how may I help you?
So how can analyze the circuit if there was more than one power source?
If there were more than one source, we would have to use KCL, KVL. So if there were resistor combinations that could be made, we could do that. But we would more likely go back to KCL, KVL, and things like that for the whole thing. It just depends on where that source is located as to whether or not there are any combinations that can be made. What we're going to talk about for the first topic on Monday's lecture is combining voltage sources. Then we're going to talk about combining current sources. And then we're going to talk about some tricks and shortcuts and stuff like that. So.